Creating a redox table. Creating a redox table of reduction half reactions frequently crops up in exams. Usually, you're given several chemical equations and information about whether a pair of reactants in each equation react spontaneously or not. Here, we'll make things a little more tricky. You have to derive the equations yourself from a table of data. Along the top row, there are 4 hypothetical ions. Down the first column, hypothetical metals. The cells of the data table contain either an X, meaning no reaction takes place between metal and ion, or a check mark, meaning a reaction does take place. For example, there's no reaction between the B ion and the C metal. That is, products are not formed, or the reaction is not spontaneous. But a reaction between the D ion and the B metal is spontaneous, and we can expect products. Notice we never see reactions between a metal and its own ion. A redox table is made up of reduction half reactions with the substance most readily reduced, the strongest oxidizing agent, indicated at the top left, and the most readily oxidized, the strongest reducing agent, at the bottom right. Taking the A ion first, having it gain an electron to become an A metal, has us write the equation as a reduction half reaction, the A ion being reduced to A metal. The other half reactions are similarly listed. At this stage, they are merely in alphabetical order, out of convenience, and not in any order related to their degree of reactivity. That's the next bit. It doesn't matter what we start with. I'll choose A ion reduction half reaction. The data table indicates that the A ion only reacts with the B metal, not with C metal or the D metal. Recall that to indicate on a table a redox reaction will occur, the oxidizing agent, the substance being reduced, in this case the A ion, must be positioned above the reducing agent, the substance being oxidized, in this case the B metal. The top left, bottom right orientation of oxidizing agent and reducing agent on a redox table tell us these two will react. And as confirmed by the data table, the B ion does not react with the A metal. The C ion, according to the data table, reacts with B metal and the D metal, but not with the A metal. So looking at the A and B equations I've already arranged, that means the C ion must be positioned above the B metal, because it reacts with the B metal, but below the A metal, because it doesn't react with the A metal. So where does the D equation go? The D ion reacts with everything except its own ion. It gains electrons from all the metals. Therefore, it's the strongest oxidizing agent and sits at the top left of the table. The D ion reacts with all metals, and the D metal does not react with anything. From this table of reduction half reactions, we can easily see that the D ion is the strongest oxidizing agent, and that the B metal is the strongest reducing agent. Another way data can be presented so that you can create a redox table is by way of a series of chemical reactions, showing either products if the reaction is spontaneous or no products if the reaction is not spontaneous. Here there are 3 net ionic equations featuring 4 different hypothetical ions and elements, so we need to put together 4 reduction half reactions. Hypothetical ions and elements are often used to have you not look at the redox table in your data book and to make you create your own redox table. In this case, all the reactions show products, so you can assume all the reactions are spontaneous. If these equations were presented as full or complete chemical equations, convert them to net ionic equations before beginning. For no other reason than it's the first atom I come across, I'll write down the reduction half reaction for the Y atom. Notice the ion is on the product side this time. Don't always assume that the ion is on the reactant side. In many reduction half reactions, ions can be found on both sides of the reduction half reaction, as will happen with the X and Q atoms in this example. So please be comfortable with knowing how to write reduction half reactions, where the reactant is a positive ion, a negative ion, or an element. The Y2 element reacts with the X2 plus ion, so the X2 plus ion must be positioned below the Y2 half reaction. This orientation is consistent with the first equation. Next, the equation that references either of the two half reactions we've just written is the third one. I can't use the second equation just yet because I would have no idea where either P or Q atoms would be in relation to the X and Y atoms. So looking at the third equation, the P ion reacts spontaneously with the Y ion. This would put the P ion above the Y ion. And this orientation is consistent with the third equation. Finally, in the second equation, the P element reacts spontaneously with the Q2 negative ion. So this ion needs to be positioned above P. And this orientation is consistent with the second equation. So the 2 negative ion is the strongest oxidizing agent and is most readily reduced. And the X2 positive ion is the strongest reducing agent and is the most readily oxidized. Notice that the only coefficient I kept from the equations was the one for the Y ion, because it's clear from the equation that Y2 is a diatomic element. It would be incorrect to write any polyatomic elements as just individual atoms. All the other coefficients in the equation don't transfer to the reduction half reactions. They were put in the equations to balance the electrons so that the number of electrons lost by the reducing agent equals the number of electrons gained by the oxidizing agent.